This video is related to the Core 1 learning unit of the Data Visualization Educational Module. In the Introductory Learning Unit, the most widely used coordinate system for data visualization, that is the 2D Cartesian coordinate system, was presented. In the Cartesian coordinate system, the grid lines along an axis are spaced evenly both in data units and in the resulting visualization. We formally refer to the position scales in these coordinate systems as linear. While linear scales generally provide an accurate representation of the data, there are scenarios where nonlinear scales are preferred. In a nonlinear scale, even spacing in data units corresponds to uneven spacing in the visualization, or conversely, even spacing in the visualization corresponds to uneven spacing in data units. The most commonly used nonlinear scale is the logarithmic scale, or log scale for short. Log scales are linear in multiplication, such that a unit step on the scale corresponds to multiplication with a fixed value. To create a log scale, we need to log transform the data values while exponentiating the numbers that are shown along the axis grid lines. This process is demonstrated in the figure in this slide, which shows the numbers 1, 3.16, 10, 31.6, and 100 placed on linear and log scales. The numbers 3.16 and 31.6 may seem a strange choice, but they were chosen because they are exactly halfway between 1 and 10 and between 10 and 100 on a log scale. Mathematically, there is no difference between plotting the log transformed data on a linear scale or plotting the original data on a logarithmic scale. The only difference lies in the labeling for the individual axis ticks and for the axis as a whole. In most cases, the labeling for a logarithmic scale is preferable, because it allows the reader to easily interpret the numbers shown as the axis tick labels. There is also less of a risk of confusion about the base of the logarithm. When working with log transformed data, we can get confused about whether the data were transformed using the natural logarithm or the logarithm to base 10. Therefore, it is important to verify the base when working with log transformed data. All coordinate systems discussed so far use two straight axes positioned at a right angle to each other, even if the axes themselves established a nonlinear mapping from data values to positions. There are other coordinate systems, however, where the axes themselves are curved. In particular, in the polar coordinate system, we specify positions via an angle and a radial distance from the origin, and therefore the angle axis is circular as shown in this figure. In figure A, 3 data points shown in a Cartesian coordinate system. The same 3 data points are shown in a polar coordinate system in figure B. We have taken the x-coordinates from figure A and used them as angular coordinates, and the y-coordinates from figure A and used them as radial coordinates. The circular axis runs from 0 to 4 in this example, and therefore x equals 0 and x equals 4 are the same locations in this coordinate system. Polar coordinates can be useful for data of a periodic nature, such that data values at one end of the scale can be logically joined to data values at the other end. For example, consider the days in a year. December 31st is the last day of the year, but it is also one day before the first day of the year. If we want to show how some quantity varies over the year, it can be appropriate to use polar coordinates with the angle coordinate specifying each day. Let's apply this concept to the temperature normals discussed in the introductory learning unit. Because temperature normals are average temperatures that are not tied to any specific year, December 31st can be thought of as 366 days later than January 1st. Temperature normals include February 29th, and also one day earlier. By plotting the temperature normals in a polar coordinate system, we emphasize the cyclical property they have as shown in the figure in this slide. The polar version highlights how similar the temperatures are in City 4, City 3, and City 2 from late fall to early spring. In the Cartesian coordinate system, This fact is obscured because the temperature values in late December and in early January are shown in opposite parts of the figure and therefore don't form a single visual unit. A second setting in which we encounter curved axes is in the context of geospatial data, for example maps. Locations on the globe are specified by their longitude and latitude. But because the Earth is a sphere, drawing latitude and longitude as Cartesian axes is misleading and not recommended. Instead, we use various types of nonlinear projections that attempt to minimize artifacts and that strike different balances between conserving areas or angles relative to the true shape lines on the globe. In this figure, a map of the world is shown in 4 different projections. The Cartesian longitude and latitude system maps the longitude and latitude of each location onto a regular Cartesian coordinate system. This mapping causes substantial distortions in both areas and angles relative to their true values on the 3D globe. The interrupted good Homolocene projection perfectly represents true surface areas, at the cost of dividing some land masses into separate pieces, most notably Greenland and Antarctica. The Robinson projection and the Winkel-Tripel projection both strike a balance between angular and area distortions, and they are commonly used for maps of the entire globe. In many different visualization scenarios, we represent data values by the extent of a graphical element. For example, in a bar plot, we draw bars that begin at 0 and end at the data value they represent. In this case, the data value is not only encoded in the endpoint of the bar but also in the height or length of the bar. If we drew a bar that started at a different value than 0, then the length of the bar and the bar endpoint would convey contradicting information. Such figures are internally inconsistent, because they show 2 different values with the same graphical element. Contrast this to a scenario where we visualize the data value with a dot. In this case, the value is only encoded in the location of the dot but not in the size or shape of the dot. Similar issues will arise whenever we use graphical elements such as bars, rectangles, shaded areas of arbitrary shape, or any other elements that have a clear visual extent which can be either consistent or inconsistent with the data value shown. In all these cases, we need to make sure that there is no inconsistency. This concept has been termed as the principle of proportional ink. We can broadly subdivide the graphical elements in any visualization into elements that represent data and elements that do not. The former are elements such as the points in a scatter plot, the bars in a histogram or bar plot, or the shaded areas in a heat map. The latter are elements such as plot axes, axis ticks, and labels, axis titles, legends, and plot annotations. These elements generally provide context for the data and/or visual structure to the plot. When designing a plot, it can be helpful to think about the amount of ink, as discussed in previous paragraph, used to represent data and context. A common recommendation is to reduce the amount of non-data ink, and following this advice can often yield less cluttered and more elegant visualizations. At the same time, context and visual structure are important, and overly minimizing the plot elements that provide them can result in figures that are difficult to read, confusing, or simply not that compelling. The idea that distinguishing between data and non-data ink may be useful was popularized by Edward Tufte. Tufte introduced the concept of the data-ink ratio, which he defined as the proportion of a graphic's ink devoted to the non-redundant display of data information. He then suggests, to maximize the data-ink ratio. It has to be mentioned that if we interpret the phrase maximize the data-ink ratio to mean remove clutter and strive for clean and elegant designs, then it is reasonable advice. But if we interpret it as do everything you can to remove non-data ink, then it will result in poor design choices. If we go too far in either direction, we will end up with ugly figures. However, away from the extremes there is wide range of designs that are all acceptable and may be appropriate in different settings. The purpose of data visualization is to convey information and make a point. To reliably achieve this goal when preparing visualizations, we have to place the data into context and provide accompanying titles, captions, and other annotations. We will now discuss how to properly title and label figures, as also how to present data in table form. One critical component of every figure is the figure title, and every figure needs the title. The purpose of the title is to accurately convey to the reader what the figure is about, what point it makes. The underlying principle is that a figure can have only one title. Either the title is integrated into the actual figure display, or it is provided as the first element of the caption underneath the figure. If a publication is laid out such that each figure has a regular caption block underneath the display item, then the title must be provided in that block of text. For this reason, in the context of conventional book or article publishing, we do not normally integrate titles into figures. Figures with integrated titles, subtitles, and data source statements are appropriate. However, if they are meant to be used as standalone infographics or to be posted on social media or on a web page without accompanying caption text. Just like every plot needs a title, axes and legends need titles as well. Axis titles are often referred to as axis labels. Axis and legend titles and labels explain what the displayed data values are and how they map to plot aesthetics. An example of a bubble plot where all axes and legends are appropriately labeled and titled is depicted in the figure in this slide. In this plot, the axis titles clearly indicate that the x-axis shows body mass in grams and the y-axis shows head length in millimeters. Similarly, the legend titles show that point coloring indicates the bird's sex and point size indicates the bird's skull size in millimeters. For all numerical variables, body mass, head length, and skull size, the relevant titles not only state the variables shown but also the units in which the variables are measured. This is good practice and should be done whenever possible. Categorical variables, such as sex, do not require units. Tables are an important tool for visualizing data. Some key rules for table layout are the following. Do not use vertical lines. Do not use horizontal lines between data rows. Horizontal lines as separator between the title row and the first data row or as frame for the entire table are fine. Text columns should be left aligned. Number columns should be right aligned and should use the same number of decimal digits throughout. Columns containing single characters are centered. The header fields are aligned with their data. For example, the heading for a text column will be left aligned and the heading for a number column will be right aligned. The figure in this slide depicts examples of poorly and appropriate formatted tables. In Figure A, the table violates numerous conventions of proper table formatting, including using vertical lines, using horizontal lines between data rows, and using centered data columns. In Figure Beta, the table suffers from all problems of table alpha, and in addition it creates additional visual noise by alternating between very dark and very light rows. Also, the table header is not strongly visually separated from the table body. In Figure C, the table is appropriately formatted with a minimal design. In Figure D, colors can be used effectively to group data into rows, but the color differences should be subtle. The table header can be set off by using a stronger color. When authors draw tables with horizontal lines between data rows, the intent is usually to help the eye follow individual lines. However, unless the table is very wide and sparse, this visual aid is not normally needed. The cost of horizontal, or vertical, lines is visual clutter. Compare, for example, Figure A and Figure C. Figure C is much easier to read than Figure A. If we feel that a visual aid separating table rows is necessary, then alternating lighter and darker shading of rows tends to work well without creating much clutter, as is depicted in Figure D. Finally, there is a key distinction between figures and tables in where the caption is located relative to the display item. For figures, it is customary to place the caption underneath, whereas for tables it is customary to place it above. This caption placement is guided by the way in which readers process figures and tables. For figures, readers tend to first look at the graphical display and then read the caption for context, hence the caption makes sense below the figure. By contrast, tables tend to be processed like text, from top to bottom, and reading the table contents before reading the caption will frequently not be useful. Hence, captions are placed above the table. Color can be an incredibly effective tool to enhance data visualizations. At the same time, poor color choices can potentially ruin an otherwise excellent visualization. Color needs to be applied to serve a purpose, it must be clear and it must not distract. One common mistake is trying to give color a task or process that is too big for it to handle, by encoding too many different items in different colors. A typical example is shown in this figure, where it depicts population growth versus population size for all 50 U.S. states and the District of Columbia. As can be seen, it was attempted to identify each state by giving it its own color, however, the result is not very useful. Even though we can guess which state is which by looking at the colored points in the plot and in the legend, it takes a lot of effort to go back and forth between the two to try to match them up. There are simply too many different colors, and many of them are quite similar to each other. Even if with a lot of effort, we can figure out exactly which state is which, this visualization defeats the purpose of coloring. Therefore, it is critical to use color to enhance figures and make them easier to read, not to obscure the data by creating visual puzzles. As a rule of thumb, qualitative color scales work best when there are 3 to 5 different categories that need to be colored. Once we reach 8 to 10 different categories or more, the task of matching colors to categories becomes too burdensome to be useful, even if the colors remain sufficiently different to be distinguishable in principle. For the dataset of the previous figure, it is probably best to use color only to indicate the geographic region of each state and to identify individual states by direct labeling, for example by placing appropriate text labels adjacent to the data points as is the figure shown in this slide. Even though we cannot label every individual state without making the figure too crowded, direct labeling is the right choice for this figure. In general, for figures such as this one, we don't need to label every single data point. It is sufficient to label a representative subset, for example a set of states we specifically want to call out in the text that will accompany the figure. We always have the option to also provide the underlying data as a table if we want to make sure the reader has access to it in its entirety. A second common problem is coloring for the sake of coloring, without having a clear purpose for the colors. As an example, consider the figure shown in this slide, which presents the same information by coloring the bars according to geographic regions, see Part A, and coloring the bars creating a rainbow effect, see Part B. This may look like an interesting visual effect, but it is not creating any new insight into the data or making the figure easier to read. Besides the gratuitous use of different colors, Figure B has a second color-related issue. Specifically, the chosen colors are too saturated and intense. This color intensity makes the figure difficult to look at. For example, it is difficult to read the names of the states without having our eyes drawn to the large, strongly colored areas right next to the state names. Similarly, it is difficult to compare the endpoints of the bars to the underlying grid lines. In the introductory learning unit, 2 critical conditions for designing sequential color scales that can represent data values were presented. The colors need to clearly indicate which data values are larger or smaller than which other ones, and the differences between colors need to visualize the corresponding differences between data values. Unfortunately, Several existing color scales violate one or both of these conditions. The most popular such scale is the rainbow scale shown in this figure. It runs through all possible colors in the color spectrum. This means the scale is effectively circular, the colors at the beginning and the end are nearly the same, dark red. If these two colors end up next to each other in a plot, we do not instinctively perceive them as representing data values that are maximally apart. In addition, the scale is highly non-monotonic. It has regions where colors change very slowly and others where colors change rapidly. This lack of monotonicity becomes particularly apparent if we look at the color scale in grayscale as depicted in the figure in this slide. From left to right, the scale goes from moderately dark to light to very dark and back to moderately dark. In addition, the changes in lightness are very non-uniform. The lightest part of the scale, corresponding to the colors yellow, light green, and cyan, takes up almost a third of the entire scale, while the darkest part, corresponding to dark blue, is concentrated in a narrow region of the scale. It is a good practice to pay attention to the axis labels, axis tick labels, and other assorted plot annotations. Chances are they are too small, since nearly all plot libraries and graphing software have poor defaults. For example, the axis labels, axis tick labels, and legend labels in Figure A are all small. We can barely see them, and we may have to zoom in to read the annotations in the legend. An improved version of this plot is shown in Figure B. It is well balanced, the text is clearly visible, and it fits with the overall size of the figure. In the Core 1 Learning Unit, some effective ways to encode information and visualize data were presented. Specifically, the available nonlinear scales and curved axes were discussed, allowing the appropriate representation of various data sets. The principle of proportional ink and the data-ink ratio were also discussed. Finally, recommended formulations of the various plot annotations as also common pitfalls of color use were highlighted. This is the end of the Core 1 Learning Unit. Thanks for watching this video.